in most of the IC applications, integrated circuit applications, we have adjacent P and N type regions, right? I mean, the single crystal silicon semiconductor is doped by both P type and N type impurities. Okay? It's not like an intrinsic semiconductor where you're just doping it by a trivalent impurity or a pentavalent impurity. It's not a single P type or N type semiconductor single crystal. It has both the regions. Okay. So one important concept to remember is that in most IC applications, the entire semiconductor material is a single crystal with one region doped by P type, and the adjacent region is doped with N type impurity. Okay, so you in this figure you can see, assuming uniform concentration of donor and acceptor impurities. So we have this P type region. Okay, where this N subscript A over here is indicating the acceptor impurity concentrations. Then we have the donor concentrations ND over in the N-type region. And assuming thermal equilibrium conditions in both the regions, we can evaluate the minority carriers, okay, from the total concentration in a semiconductor Ni square, right? We can evaluate what is the minority concentration. For example, in N-type, the minority carriers are holes. Okay. Similarly, for P-type, the minority carriers are the electrons. All right. So now, what happens is that we have a gradient, right? So this gradient exists at the interface, at the metallurgical interface between P-type and N-type regions. The gradient is with regards to the doping concentration in both the P-type and N-type region, and due to that, there's going to be a diffusion, okay, from P-type P-type semiconductor to N-type. So there are going to be holes that are going to be flowing from P region to N region, and similarly there will be a diffusion from, likewise there will be a diffusion from N region to P region. Okay, so this process, what it does is it tends to create a sort of an interface which is going to produce a space free charge region, okay, in which there are no charge carriers, there are no electrons and no holes owing to the recombination. But what they're going to do is, in that region, okay, they're going to create a region over here, and they're going to produce, for example, in the N-type region, we're going to have immobile, positively charged ions which are fixed, which are not going to conduct any current, and on the other side we are going to have negatively charged acceptor impurity like boron or trivalent impurities, okay, which have already accepted electrons. So what we're going to have is negative and positive ions on either side of P-type and N-type. So on N-type we are going to have positively charged donor impurity atoms, and on the P-type we are going to have negatively charged acceptor atoms. And due to these ions which are fixed in the lattice, they are not going to conduct any current. There are no charges. There will be an electric field. There will be an electric field from N to P, directed from N to P, and this electric field is going to produce a force that is going to halt the diffusion of, or stop the diffusion of charge carriers from P-type to N-type region and from N-type to P-type region, because the direction of electric field is directed as such. The negative particles cannot, go on and diffusing themselves to the P-type region from N-type semiconductor region, and similarly from P-type the holes cannot go on and diffuse towards the N-type region. So this process is halted by the establishment of this electric field, and an equilibrium condition is again established. Okay, so you see in figure 1.1 is a simplified block diagram of a PN junction, and 1.1b shows respective P and N-type doping concentrations. So if you assume uniform doping in each region as well as the minority carrier concentrations, which is evaluated assuming thermal equilibrium conditions, They are they can be evaluated from such conditions, but owing to this, gradient, doping gradient that exists at the interface, at the metallurgical interface at x equal to 0, you're going to have diffusion, and this diffusion is going to create or produce a barrier, let's say a depletion region which is charge free, right? There are no charges, and the electric field that is going to be produced due to the ions that has been uncovered, they're going to stop this process of diffusion, okay? And we are going to reach the steady state thermal conditions back again. So let's have a look at this whole diffusion process and electron diffusion process. This figure 1.1a shows the initial diffusion of electron and holes across the metallurgical junction at the instant in time that P and N regions are joined together. So this process is blocked once the electric field is established, and this electric field, if you recall, is going to have a direction like this from N-type to P-type region. The reason being that the donor impurities are positively charged. For example, it could be a phosphorus atom, okay, antimony, arsenic, whatever. Alright. So I mean, you are going to have an array of such in this region. You're going to have an array of such ions which are not themselves contributing to the current. And similarly, you're going to have, for example, if there is boron doped on the P-type region or any group 3 element, you're going to uncover these negatively charged ions, and the direction of electric field is from positive to negative, which is going to hold back the diffusion of holes and electrons from either side. So initially there is a diffusion of holes from P region into N region, and the diffusion of electrons from N to P, which is shown in figure 1.11. Now the flow of holes from P region uncovers the negatively charged acceptor ions, right? In the P region, we have the acceptor ions like boron, which have to take electron to stabilize its octet structure, leaving behind the holes which are the majority carriers, right? So, and similarly, the flow of electrons from N region uncovers the positively charged donor ions like phosphorus. So this action creates a charge separation, which is shown in figure 1.12, and this sets up an electric field oriented in that direction from positive to negative. So you see, this is what is going on. So you are uncovering positive charges. This is the direction of field, right? So in the N-type region, you have the positive, let's say, group 5 impurity atoms, right? They are fixed. They are the part of lattice now, but they are not going to conduct any current. All they are going to do is to establish an E field of force, which is going to stop the process of diffusion, right? So this creation of barrier potential is halting the diffusion, right? And due to this E field, there exists a barrier potential, which is called VBI, and that's going to stop. It's a force that's going to stop the diffusion process. All right. So basically, this region is space-free region. You call this as depletion region, or in the context now space charge region. So there are no mobile charges. There is no conduction of current, right? And the thermal equilibrium conditions are reached when the force balances this diffusion concentration gradient, the diffusion concentration gradient, which is responsible for the diffusion of holes and electrons on either side. Okay, so once they are balanced, you have the thermal conditions back. So P-N junction in thermal equilibrium is shown in figure 1.12. The space charge region with negatively charged acceptor ions in the P region and a positively charged donor ions in the N regions. Resulting electric field is from N to P. So the potential through the junction and the built-in barrier potential is shown in part B of the figure. Okay, and this barrier potential is responsible for halting the diffusion process. Okay. Now, so if no voltage is applied to the P-N junction, the diffusion of holes and electrons must eventually cease. Well, that has to be the case. It cannot go on forever. The direction of induced electric field will cause the resulting force to repel the diffusion of holes and from the P region and diffusion of electrons from the N region. So what it says is that you see you have this directed E field. Okay, so this is positive and this is negative. The holes cannot go on, diffusing themselves from P to N region anymore. because of the force they are going to, repulsive force they are going to experience of from the established electric field. Similarly, electrons, cannot go on this direction because of the repulsive forces they are going to, a repulsive electric field they are going to experience force that has been established in the depletion charge region. Okay, so this diffusion process is eventually is going to halt. So thermal equilibrium occurs when the force produced by the electric field and the force produced by the density gradient they exactly balance out each other. The two forces, they balance out each other and you have the thermal equilibrium. Now the positively charged region and the negatively charged region comprise of space charge region or depletion region of p-n junction, in which there are essentially no mobile electrons and holes. So because of the E field in the space charge region, there is a potential across that region, which we have shown in this figure 1.12b. And this potential difference due to this E field is called the built-in potential barrier or built-in voltage. That is, an intrinsic property of a semiconductor which has been doped. And you see, the reason for this establishment of electric field is due to the uncovering of positively charged ions on the N-type region and the negatively charged ions in the P-type region, right? So due to this donor concentrations Na and Nb on either sides and assuming thermal equilibrium conditions, we have this barrier potential which can be expressed in terms of Boltzmann constant, temperature, and the charge, and this quantity turns out to be, this is the thermal voltage, which is about 2.6 millivolts at the room temperature of 300 kelvins. So Na and Nd are responsible for establishing this barrier potential and the electric field, and they are the net acceptor and donor concentrations in the P and N regions respectively, right? So usually this turns out to be, it's a logarithm function, so it doesn't matter the magnitude of acceptor and donor impurity, how much it is. It turns out to be a small value in like 0.6, 0.7 volts for typical silicon, single crystal silicon crystal, which has been doped in, let's say, 1 in 10 to the power 6 in both, let's say, in such orders in P-type and N-type regions, right? So it turns out to be a small value on logarithmic scale. Now, this example shows the calculation of a built-in potential of a p-n junction, and if you consider silicon at room temperature, which has been doped by the acceptor is about 10 to the power 16 per cubic centimeter, and the P region, and then the donor is about 10 to the power 17 in the N region. So if you plug those values in this relationship with the thermal voltage, you find out the barrier potential is of the order 0.757 volts at room temperature. Now, because of the log function, the magnitude of VBI is not a strong function of doping concentrations, right? It's not a very huge value. So therefore, the value of barrier potential of silicon p-n junction is usually within 0.1 to 0.2 of this calculated value. So in a sense, VBI maintains the equilibrium, so no current is produced by this voltage. That's why it is barrier potential, because it halts any current due to the majority carriers flowing from one region to another region. So, however, the magnitude of VBI becomes important when we apply the forward bias voltage. Okay, so that's all for the p-n junction in this part of the video. So we're going to discuss the forward and reverse bias in the next upcoming lecture videos. Okay, that's all.